In today's video, we'll be covering Power Mux circuitry, involving theory and real-world applications with the breakout board that I designed. I'll showcase both versions of the PCB along with the results I obtained from my oscilloscope. Let's consider the following scenario. You have multiple sources at your input and one source at your output tied to your load. There's a couple different ways you could go about this, one of which is either connecting your sources or batteries together with no isolation, either in series or parallel. This can cause a lot of issues as batteries in series or voltage sources in series can cause a higher or lower voltage output, and this just depends on how you configure your batteries at your input. Batteries in parallel or voltage sources in parallel need a BMS system to ensure that the voltage is the same across each node. If it's not, then one of your batteries could potentially be damaged and no longer usable. You could use some sort of switch as seen here, like a single pole double throw. However, this can increase the size of your PCB, as if you have a heavy load attached to your circuit, say something that takes up 1.2 to 2 amps, you'll need a large switch in order to withstand this amount of current. You could also then use a comparator circuit. However, again, comparators are limited to how much current they can handle with a given load. So comparators can't really handle 3, 4, 5 amps of current, and that's where a Power Mux would come into play. So let's take a look at the functional block diagram and see how it works exactly. Here is a generic example of a functional block diagram of a Power Mux. I want to make it clear that not every Power Mux needs a microcontroller in order to be controlled, nor does every Power Mux have an internal N-channel FET. They could use P-channel FETs or other types of semiconductor devices. But in this case, this is the example that I'm showing. So this block diagram has 2 input sources, 2 enable pins, and 1 output. And basically, if a high signal is sent on the enable pin to the gate of the FET, and if this voltage is equal to the drive voltage or higher of the FET, current can flow from drain to source, and then whatever will be the voltage at the input will be seen at the voltage at the output. Now, the ideal diode controller is used to keep the voltage as close to the input sources as possible. There will be a slight drop off, but again, it's just to keep it as consistent as possible. So if you have 5 volts here, you should have basically 5 volts at the output, give or take. And the microcontroller either sends a high or low signal. If a low signal is sent to the enable pin, current will not flow from drain to source. And if neither sources are valid, then there will be 0 volts at the output. Now let's look at the Power Mux that I chose for the breakout board. Here is the product information page from Digikey of the TPS2121RUXT. We could see that the price of this is fairly on the expensive side, though if you're short on board space and you need separation between higher voltages such as 10 and 15 volt sources, this is definitely a good IC to choose, as it has a pretty wide voltage supply range along with current output up to 4.5 amps. We could also see here that the FET type is set to N channel. As discussed earlier, this will not always be the case, again depending on what part you choose from Digikey and the filters that you put on it. This will ultimately determine what part that you end up searching for. Here on the datasheet, we can see that a lot of the information from the Digikey link is provided on the title page. The wide operating voltage range, the adjustable overvoltage supervisor, adjustable priority supervisor, the output current limit, along with the current consumption of the device being at 200 microamps, which is very low, and the applications that you could use this IC for. Here is the typical application schematic of the TPS2121. Now, here you could see that it's fairly simple with 2 power sources, some resistors essentially creating a voltage divider along the PR1, OV1, and OV2 pins. We also have a microcontroller dependent on the select pin, and this will then determine which source is selected for the output. If the voltage at PR1 is higher than the voltage set at IN2 internally in the chip, power source 1 will be your output. However, if it's lower, then power source 2 will be your output. If neither source is high enough to drive the chip, the output voltage will be 0. And we'll look further into the datasheet to see what voltage is needed in order for an output voltage to be present. Here are the two types of packages for this available IC. The TPS2120 is in a BGA package, while the TPS2121 is in a VQFN package. This is the package that I chose for the project, as BGAs can be a pain to solder and just add unnecessary complexity to a simple breakout board. If a BGA really is needed, then use it in your project. However, I haven't reached that point yet when making PCBs. But if we look at the pin functions table, we could see the pin description and name of each pin for our IC. So we have our input pins, output pin, our status output indicating which channel is selected, which again is very important, the ILIM pin, which limits the amount of current that comes out of the Power Mux, the SS pin, which adjusts the input settling delay time. This isn't really important for what I'm trying to use it for. However, if you have something that is very time and frequency dependent, this is where this pin would be very useful. And you also have the OV1 and OV2 pins. So these pins essentially protect the IC against overvoltage cases. So if you don't want your voltage to exceed a certain value, if the internal reference voltage is higher than what is expected, the Power Mux will not output anything. And you could actually set this with the external resistors that you use for the voltage divider on the OV1 and OV2 pins. So again, this IC can protect against overvoltage cases, and it also won't output anything if the voltage is too low. So there's a lot of features that could be really useful for this, and in my opinion, it's worth the extra cost. Further down in the datasheet, we can see the functional block diagram, and it's very similar to the example that I showed you previously, with the main difference being some extra comparators, a couple more MOSFETs, along with a current source that is set internally. Now, I will provide a link to the datasheet along with the part that I used for this breakout board, as I feel that there's not enough time to cover every aspect of what's included in this IC along with the respective datasheet. There's a lot of detailed information with graphs and implementation for a given application. So I think it's really important to spend the extra time to read it. And again, this video is more just a basic overview of how to use this part. Also here we could see the active current limit. This is one of the formulas that I ended up using to determine the resistors that I needed. And if we look under the application and implementation section, this is where I found the resource that I wanted to use for my given example. So it's slightly different than what is shown here, but basically you have a 5 volt source, and instead of a 3.3 volt source, you have a 3.7 volt source. And again, as you can see here, as I mentioned earlier with the resistors, depending on what resistor values you choose here, this will determine when this OV1 internal reference source is set off to either keep the system on or off. And again, if it exceeds that value, that's when the output will be 0 volts. Now, you don't have to use a microcontroller in order to select which source to use. This is why this is called the manual switchover. The automatic switchover can be seen a little bit further down here. And above, again, we could see some important formulas in order to determine the resistors that you need to set the internal voltages for each pin. And once again, this is just a basic voltage divider. So if you have 5 volts here, you just need to determine what voltage you want at the 5 kilo ohm resistor. So setting the top resistor will ultimately determine what internal reference voltage you want to set off. We're now ready to look at the schematic. Regarding the schematic, we can see not much has changed from the application example, except for a voltage divider that I set here for the 3.3 volt microcontroller source. So from my understanding of the datasheet, it seems as if IN2 is the primary output. So if you have a 5 volt source, a 3.7 volt source, and a microcontroller set to the CP2 pin instead of tying it to ground, IN2 will be the primary output. However, I wanted IN1 to be the primary output. So what I did was take that 3.3 volt source, cut it in half to 1.65 volts with a voltage divider with two 1K resistors, and then set that as my voltage reference for the CP2 pin. The only problem that I didn't realize was the voltage reference that I was setting at my 5 volt source, or IN1, was also equal to 1.65 volts. And that voltage needs to be higher than the voltage at CP2, otherwise IN2 will still be the primary output. So I had to make R2 either 10K or 9K and less than or equal to that value in order to actually get a higher reference voltage than the 1.65 volts seen at the 3.3 volt source. So that was something that I just had to do through some testing and experimentation. Also, the V reference voltage for OV1 and OV2 is extremely important, as if you exceed the 1.06 internal reference voltage, there will be 0 volts at the output of the Power Mux. So that's the note that I put here. And the under voltage lockout for this device is also set to 2.5 volts, which can be seen under the electrical characteristics table in the datasheet. Now, another thing I wanted to mention as well in terms of component organization, something I started doing was adding the part number, price, and Digikey link. I feel it makes parts a lot easier to purchase and order and to just keep track of everything needed for the bill of materials, because there's been a lot of times where I've ordered parts and I'm always missing or forgetting something. So this is just another way to organize your schematic. Another thing I wanted to mention regarding the Power Mux itself, if we look at the pin configuration and functions section as we saw earlier, when I was making a footprint for this, I copied the bottom view of the IC. This is a problem because when you have footprints and you're essentially setting the pins that are going to be set for each square that you make on the chip itself, you need to make sure that you're doing it against the top view, otherwise everything will be inverted. So when I was testing the original board that I made, I was getting an output voltage without having the given condition to get one, and that was because 1 and 8 were swapped along with 2 and 7, and this entire column of pins were swapped with these. So the entire thing was wrong, and I tried using a hot air gun to remove the chip, but I think the hot air gun that I bought for cheap a couple years ago is no longer good, so I decided to just make a second version of the PCB. But other than that, the schematic again is fairly simple. You just have some test points, some resistors that set voltage dividers. If you're not familiar with the voltage divider, you basically just find the voltage across this resistor here, R4, so it's 5K divided by 5K plus 10.2K, and then you multiply that by your source voltage, and that will give you the voltage reference. And here we just have a note again regarding the current limit that I set for this breakout board. So it's set at about 1.72 amps. Not that I will ever even get remotely close to that threshold, but it's just something that I figured a higher current doesn't really hurt for this, especially if someone wants to use this breakout board for higher load applications. And I also have a pad, once again, for an easy access to ground, or if I need to probe this circuit with an oscilloscope. Let's take a look at the PCB. The PCB I designed for this demonstration is a 2-layered PCB with the front and back copper plane as ground. The 3D view here shows that there's not really much going on. We have the 2.54 millimeter jumpers, and these are surface mount versions, as I wanted to keep everything surface mount and not have to use any through-hole parts. The resistors and capacitors that I used are 0603, and the IC itself, again, is the VQFN package. The back of the board just has the JLC number placement along with the month and year it was created. And the actual layout itself is not too critical. We're not dealing with high speed, high frequency design here. It's mainly just power sources and voltage references within the chip. So the only thing that I did that was kind of important was the actual traces themselves. I first started with a thin trace to fit within the width of the given pad, and then as soon as I could, I made the trace fatter. So I started with a 0.2 millimeter trace followed by a 0.5 millimeter trace, and I also put the resistor to limit the amount of current and the SS pin for the capacitor as close as possible to the IC. Now the datasheet itself also gives you a good example of how you want things laid out, along with via placement if you are using this IC for higher current applications. Again, for this demonstration, it's really not necessary for what I'm trying to accomplish, but if you do need to know what is needed for that, it is provided in the datasheet. And reference designators are as close to their part as possible, along with the test points. And once again, the scope pad from the MQ2 gas sensor board was just copy and pasted because there's no need to remake a footprint. If you have a known good footprint, don't reinvent the wheel. Just use it in another project if you need to. It will save you a lot of time. And also just keep in mind when you choose pin headers, make sure the part that you order matches with the pin 1 reference designator. So if we look at the connector here and we search up the Digikey link, here if we go on the datasheet for this particular part, we can see how it's oriented. And you just want to make sure that the pins here line up with the footprint. Now, unfortunately, the footprint that I selected, it was reversed, so I had to bend the pins slightly. Not really a big deal. Thankfully, I didn't have to reorder the board a third time, but just something I wanted to mention as it is fairly easy to mistake. So just make sure you read your data sheet and see how the actual pin is configured, which in this case, your pin 1 is on the right and not on the left as I selected here. So here's the setup as promised. Over here we have the breakout board with 3 main voltage sources. The 5-volt source, which is red, which is coming from our power supply. The 3.3 source from our microcontroller. This is tied directly to the 3.3 volt pin instead of using the GPIO outputs. But in the code, you'd basically just set the pin high, so it's very basic. And then we have 3.7 volts coming from a buck converter that I designed a couple years back. And I just set the pot RV1 to output 3.7 volts with the other resistor being at a fixed value. Right now, if we look at the scope, here we could see the mean of the channel that we're measuring, which is channel 1, is 5.16 volts, which is about what is on the supply. Channel 2 I have tied to the output of the buck converter, so we have a mean of 3.74 volts, which is about expected. If I remove the microcontroller source, it's still at 5, and if I remove the 5-volt source, it goes back down to 3.8 at the output. And if I start reducing the voltage on the supply, we can see now it's at 3.8. And if I raise it to about 6.2, or it seems to be at 6, it drops to 3.8. And the same can be said for the other protection. If you raise it above the V-sense, the supply will drop. And if we reduce this to say 2.5 and remove the 3V7 source, see right now we have no voltage. If I raise it above to 2.91, now we have the channel again set. It's a little hard to see, but basically the yellow channel represents the output and the purple is the buck converter. As always, thank you guys so much for watching my content. I'm trying to now post on a fairly regular basis, at least every 2 to 3 weeks. I'm planning on covering PCB design along with firmware. I do have a couple of big projects that I want to work on after I finish the gas sensor, and I will definitely be showing that on the channel. So be sure to stay tuned for that. And if there's anything that you feel that I can improve upon, whether it be my content creation or how I explain circuits, feel free to let me know in the comments below. But anyways, thank you all for watching and have a great day.